December 22nd, 1915. A man is lying in a muddy trench on the eastern front of a world at war. His name is Karl Schwarzschild. He is 42 years old. He is one of the most respected astronomers in Germany. He volunteered for military duty at the age of 41. Nobody asked him to go. He went anyway. In that trench, he is sick. An autoimmune disease is slowly destroying his skin from the inside out. He is calculating artillery trajectories between attacks, and somehow in between all of that, he is solving the most important equations in physics. 3 weeks ago, Albert Einstein published his general theory of relativity. The copy reached the trenches, and Schwarzschild, sick and cold and surrounded by war, solved them. He found something nobody was looking for. A boundary, a point in space where gravity becomes so extreme that the geometry of space-time closes around itself permanently. A location where the escape velocity surpasses the speed of light. A place from which nothing, no object, no signal, no light can ever return. He wrote his solution in a letter and mailed it to Einstein the same day. Einstein called the solution elegant. He could not believe the thing it described actually existed. Schwarzschild died 6 months later from the disease he got in the trenches. He never got to name what he found. He never knew what would eventually be discovered inside it. And there is something inside it, something that took physicists another 50 years to even properly ask about. I will give you that question now. I will not answer it yet. When something falls across that boundary, does the universe remember what it was? Or at its most extreme, does reality simply forget? Hold on to that question. Everything in this video builds toward it. Part 1. What a black hole actually is. We have been calling it the wrong thing from the start. A black hole is not a hole. It is not an absence in space. It is the most extreme concentration of mass the universe can produce, dense enough that space and time around it stop behaving in any way your experience has prepared you for. Here is how one forms. A massive star burns for millions of years. Two forces fight each other the entire time. Nuclear fusion in the core pushes outward. Gravity pulls inward. The star holds its shape because these two forces are balanced. When the fuel runs out, the balance ends, not gradually, in less than a second. The core collapses. The outer layers crash inward, rebound, and explode outward. A supernova. A single event releasing more energy than our sun will produce across its entire 10 billion year lifetime. What remains at the center keeps collapsing, past every known threshold, down to a point where our equations break, where density becomes mathematically infinite. We call it the singularity, the place where physics as we currently understand it hits a wall and stops working. Surrounding that point is what Schwarzschild found. A boundary called the event horizon, not a physical surface you could touch. A location in curved spacetime where the geometry closes, where every possible path, including the path light takes, curves inward and never comes back out. Cross it, and there is no outward direction anymore. Not slow to escape, not difficult, impossible. You are probably thinking, fine, a drain in space, a point of no return, got it. You don't have it yet. Part 2. What actually happens to you? What happens to a person falling into a black hole is where everything your intuition expects turns out to be wrong. If you are falling toward one, freely, no engine, no resistance, you would feel nothing unusual. No dramatic force, no warning you could read. You would cross the event horizon without feeling it at all. No wall, no flash of light, no sensation marking the moment. You would cross the most extreme boundary in the known universe, and you would not know it happened. That is not a simplification. That is what the physics requires. Now here is the part that should stop you cold. If someone watched you fall from a safe distance, they would see something entirely different. They would watch you slow down. Your image would stretch and dim. You would appear to approach the boundary, but never reach it, fading, becoming redder, appearing frozen at the edge forever. Two people, one event, Two entirely different physical realities, neither one wrong. Inside, you continue falling, and every direction you can move forward, backward, sideways, now leads toward the singularity. Not the way a magnet pulls. The way tomorrow is ahead of you. The singularity is not in front of you. It is in your future. And nothing can change your future from inside the black hole. This is not imagination. This is what general relativity, the most precisely tested theory in the history of physics, requires. Part 3. What Hawking found. In 1974, a physicist named Stephen Hawking discovered something that should have been impossible. Black holes glow, not visibly, but they emit particles slowly across time scales longer than the current age of the universe. They lose mass, they shrink. Eventually, they vanish entirely. This is called Hawking radiation. Buried inside that discovery was a consequence so uncomfortable that Hawking spent years checking his own work before accepting it was real. If a black hole eventually disappears and the radiation it emits carries no memory of what fell in, then everything that ever crossed the event horizon is gone. Not hidden, not scrambled somewhere, recoverable, erased. Now we return to the question from the beginning. When you fell through that boundary, you carried information, the complete description of your physical state, every particle, every quantum property, the specific pattern that made you distinct from every other arrangement of matter in the observable universe. Quantum mechanics, the most precisely tested framework in science, says this cannot be destroyed, ever, under any conditions. The universe keeps records. This is a mathematical requirement, not a preference. Hawking's calculation said the radiation is completely random. No memory, no trace. Drop a rock, a book, or a human being into a black hole. The radiation that eventually emerges is identical in all three cases. If the black hole is gone, and the radiation carries nothing, quantum mechanics is wrong. Not slightly, fundamentally, structurally wrong. Two of the deepest theories in physics were now directly contradicting each other. General relativity said the information is gone. Quantum mechanics said that is impossible. Both had passed every experimental test ever designed for them. They cannot both be entirely right. This is the information paradox. The question from the beginning of this video. Now you have it. Part 4. The date. In 1997, Stephen Hawking placed a formal wager with two physicists at Caltech, John Preskill and Kip Thorne. Hawking bet that information is genuinely, permanently destroyed inside a black hole. Preskill bet the opposite, that the universe's record-keeping holds even here. Thorne sided with Hawking.
The prize, an encyclopedia of the winner's choice.
You are probably thinking, a bet? This is how physicists resolve something this fundamental. It isn't. That is the point. The bet was not a resolution. It was an admission, a way of marking the exact location where current understanding runs out and mathematics alone cannot yet force an answer. For 7 years, the argument continued. In 2004, Hawking stood before an audience in Dublin and conceded. He had revised his calculation. The radiation he now believed was not perfectly featureless. Information was encoded inside it, scrambled to a degree that made it effectively unreadable, but present, conserved, required to be conserved. He sent Preskill a baseball encyclopedia because information can in principle come out of a black hole, but reconstructing it, he said, would be like burning a library and trying to read every book from the smoke. Kip Thorne refused to concede. He believed the question was not finished. He was right to hold. In 2019, two independent research groups published results pointing more strongly toward information surviving, that Hawking radiation follows the pattern quantum mechanics demands. The exact mechanism remains beyond what we currently understand. The universe keeps records. We are increasingly confident. We cannot yet explain how. Part 5. What we have seen. There is a black hole at the center of our galaxy. Its name is Sagittarius A. It contains 4 million times the mass of our Sun. Every one of the 400 billion stars in the Milky Way orbits slowly around it, including ours. In 2019, a collaboration called the Event Horizon Telescope produced the first image of a black hole shadow. Radio telescopes across 6 continents, functioning as a single instrument the diameter of the Earth, captured a ring of superheated gas glowing around the dark center, the shadow the event horizon casts on the light behind it. The light in that image had been traveling for 53 million years. We saw the boundary Schwarzschild found in a trench in 1915. But here is what that image does not show you. It does not show you what happened to anything that crossed that boundary. It does not tell you whether the universe remembered it. The most powerful observational instrument humanity has ever built shows us the edge, and everything beyond it remains mathematics and an open question. The photograph is beautiful, and it marks precisely the border of what we can see. What lies beyond that border is where the paradox lives. Part 6. Responsibility. Now hold what you have been given. A man solved equations in a trench while a war happened around him, and a disease worked through him. He found a boundary inside the mathematics. He died without knowing what it meant. A century later, we photographed that boundary from 53 million light years away. And we still do not know what happens on the other side. We are powerful enough to photograph the shadow of a black hole, and still not powerful enough to answer whether the universe keeps its own records at the most extreme conditions it produces. There have been other moments in history where the edge of understanding was located precisely where someone could say, here is what we know, here is where it ends, here is the exact question we cannot yet answer. Those moments have always been more important than the comfortable answers that came before them. We are in one of those moments now. Somewhere in the gap between general relativity and quantum mechanics in the territory where neither theory works alone, there is an answer that will require something new, a theory that does not yet exist in finished form. Someone will find it. They will be doing something that looks from the outside like an ordinary day's work. And inside that work, they will find what Schwarzschild found, something nobody was looking for. December 1915, a letter is mailed from a military hospital. A dying man had found a boundary in Einstein's equations. He did not know what was inside it. He did not know that people would spend a century arguing about whether that boundary erases information or preserves it. Everything that falls through that boundary carries something, a pattern, a record, the complete physical description of what it was, every quantum state, every connection between parts, across 13 billion years of cosmic history. The universe, we now believe, does not erase that record. Even here, even at the most extreme point, our physics can describe, even at the boundary, a dying man found in a trench while the world was burning around him. The universe does not forget. We are still working out exactly how it remembers. The boundary is real. The photograph exists. The paradox is not solved. And somewhere right now someone is working on it.